Firstly, as I promised, I have more information regarding our plans for midterm 2. So you can see this announcement likewise in your Brewing Learn account, and we can just quickly go over it. Basically, the midterm exam will cover everything after our midterm 1, which is the physical meaning of entropy and linking entropy with probability. All right, so that's where we're going to start our midterm 2. And the coverage will end on our next Monday's lecture. So hopefully we'll be able to finish conventional entropy and third law of thermodynamics. We'll see how far we go. But wherever we stop, your midterm 2 will cover all the way until our next Monday. And then when and where. So pretty straightforward. Again, depending on if your UID ends with even number or with odd number. So last time the even number stayed in this room, so this time the odd number will stay in this room. If your UID ends in even number, you'll go to Dot Hall 167. Your TA will be with you in Young Hall, and I'm going to meet you in Dot Hall. So that's where the exams are going to take place. What to expect on the exam? So everything will be pretty much the same. Open book, open note, bring your own equation sheet, periodic table, whatever you think that may come useful to you. No electronic devices are needed. But during the exam, if you feel like, oh, I just forgot what the gas constant is, and you didn't have it written down, you can always ask us. We'll just put it on the board for any of the constants you want to know. What else? So the structure of the midterm exam, that should be midterm 2, there's a typo. So last time I posted a survey after midterm 1, I think 53% of people voted for like exam being, the difficulty being okay, but a bit too long for people to finish. So I take down one short answer problem. So now you should expect 10 true and false problem and only 4 short answer problem, and likewise 1 comprehensive problem. So hopefully that gives you more time to work on the exam. Study suggestions are pretty much stays the same. We have discussion worksheet and chapter end problems you can always refer to. Again, I tell everyone, I make my midterm exam by looking at the chapter end problems. So if you master all the chapter end problems, you're pretty much guaranteed to know what to expect on the exam. And then for next week, on our Wednesday, we have our common buffer lecture or the review session. So likewise, I posted a small survey. Basically, it's 1 extra credit. Just fill in the survey and tell me which topic you feel most lost about. So I should do more reviews or practice problem with you next Wednesday. What else? Yeah, and also suggesting you to create your own equation sheet, and we offer partial credit, so do make sure you set up the calculation, and rather than spend too much time to get a numeric answer correct. And at the very end, next week, there won't be any discussion worksheet since we're having our midterm exam. Your TA will have more information regarding when the last 2 discussion worksheets will be due. And I have posted my previous midterm 2 exam. Again, there's a typo. My previous midterm 2 exam from my 23 fall quarter. So use it as you like, right? It's my previous exam, but they're longer than I expected and more difficult than I expected. So you get a gesture about the difference between the previous midterm 1 and the real midterm 1 you have. So just use it as a source of practice. You can, I don't have an answer key, but I do have a walkthrough of that midterm 2 exam. You can find it in our YouTube channel, just to the 23 fall quarter or something. All right, any administrative questions before we get started? Nope? Okay, sounds good. So as a quick review in what we covered last lecture, so I just want to start from this appendix table. So you should be able to get access to this appendix table. I'll also probably print it out and make sure you have a copy of it in our midterm 2 exam. Now, in this appendix table, there are several things, right? So last lecture, we went over this one, the standard heat of formation, and then how to use the standard heat of formation to calculate the standard heat of the reaction or standard enthalpy of the reaction. A few things that we discussed, for example, what does this little knot mean? The little knot tells us that's the standard state. So typically, a standard state is defined at 1 bar for liquid, solid, and gas. And this 298 denotes this is the standard state for temperature at 298 Kelvin. You can have different number for the standard heat of formation at different temperature, as long as we have the temperature well defined. This little form tells you that's the heat of formation, right? So basically that's the amount of energy required to form your substance from its elementary form. Now a substance of its elementary form, for example in this one, like say bromine. Sorry. Actually, let me use carbon because we use carbon. So for example, the elemental carbon, the standard state for elemental solid carbon will be in its graphite form. So this one is our standard state. And that delta HF will be 0. You can't form it from a elementary form. And the delta H for that formation process is just 0. Or the other way to put it is looking at this table, whenever you see a 0, that tells you what's the standard state of that element. So one of the questions I might be asking you is, what is the standard state for bromine, right? And you can search for it. Okay, so that's Br2 liquid. Just different ways we can ask the same question. Nevertheless, at the end of our last lecture, we raised up a question. So how do we actually measure this standard heat of formation, right? What kind of experiment do we need to set up in order to measure these numbers? So let's go back to our lecture note 16. All right, so in this lecture, we'll first go over a detailed plan. And what exactly are we doing when we're measuring the heat of formation of a some kind of substance? Let's imagine that substance being a real gas. So I'm going to copy that on the board and just to have a little bit more space to mark down what we're saying. So first of all, what we want is the measurement. So can people see my handwriting here? Okay. So we want to measure delta H naught of formation, say, of a real gas. But we also know that the standard state of a compound or a gas is like ideal gas. So there are several different steps we need to take. Let's imagine this real gas being like, say, HCl. Right. So if we write out the formation, we have H2 plus Cl2 goes to HCl. But the problem here is we're looking at H2 and Cl2 in their elementary form and standard state. So we have to take several steps. First step is we want to convert my real gas. Well, actually, let me go this way. Let me think. So first of all, let's write this one. So what we're looking at is H2 gas plus Cl2 gas go to HCl. So the first thing is we started from these ideal gas in their standard state, because right now we're talking about the standard state. So these are the elementary form of my H2 and Cl2, they must be ideal. So the first thing is we want to translate real gases to hypothetical ideal gases. Again, the whole point here is the standard state for gas is ideal, but in reality, we do not have ideal gases that we can do reactions with each other. So we must have a way to translate real gas with ideal gases. So that's the first step. Second step, now we have hypothetical ideal gases. Let's imagine that's the hypothetical ideal gases of all my reactants, right? So H2 and Cl2 now in ideal form. we want it to be reacting with each other. So naturally, we want to mix our ideal gases, H2 and Cl2. Or we need to calculate delta H for mixing of my ideal H2 gas and Cl2 gas. And we went over several different calculations of ideal gases. So mixing of ideal gases is something we are able to calculate. Next up, we want to address the difference between your enthalpy to different temperature and pressure. Or the other way to put it is we want to change the current temperature and pressure to the experimental condition. Right? So the temperature we do experiment is not necessarily at 1 bar and at 298 Kelvin. So that's the standard state. But experimentally, we might have a different setup. So we want to use the equation we derived before to address for temperature and pressure differences. With me so far? So in this case, we're calculating changes of enthalpy at different temperature and pressure. And for this one, the reaction we're using is the one we derived before. So that's delta H equals to the integration of Cp dt plus integration of V minus Tv alpha dP. All right, and this comes from, remember, the pressure dependence of enthalpy. So in previous cases, we derived dH over dP at constant T equals to negative Tv alpha plus V. That's where this comes from. The first one is just a heat capacity at constant pressure. Okay? And then, now what we have. So we started from translating the real gas into ideal gas. And then we have mixing of ideal gases. And then we're translating the temperature and pressure into the temperature and pressure so we can perform the reaction, right? So now we're ready for the reaction to take place. So this one is called calorimetry. So that's the measurement of delta H of reaction. Right, so here we actually have the reaction taking place. So that's H2 plus Cl2 go into 2HCl. And after the reaction, now we have a new set of temperature and pressure. We want to translate it back using the same reaction back to our standard state. And again, now we have real gases reacting with each other, right? The standard state for my HCl gas is also an ideal gas. So I want to translate now my real gas back to ideal gas. So we're representing the standard state of HCl. I think let me just remove this one to the other end. So this one should be hypothetical gas into real gas. This one is real gas. Go back to ideal gas. All right, so for this step, it looks like very complicated. Just think about what we have. Eventually, what we want is the delta H naught, the standard heat of formation of my HCl as an ideal gas. All right, so what we start from is the ideal gas, the hypothetical ideal gas. So this is our starting point. So from our hypothetical ideal gas of H2NCl, we first want to have a way to translate that ideal gas into real gas. So that's something we will talk about later on. Okay. Now let's just focus on this one. Focus on this calorimetry step, which is the measurement of delta H of my reaction between H2 and Cl to form HCl. So how to use calorimetry to measure the reaction enthalpy. So before we start, do you have any questions so far for the whole setup? Well, first talk about the calorimetry, and then these 3 and 5 are something we discussed before. 2 is something we discussed before. 1 and 6 is something we will discuss later on. So right now we're just going to focus on number 4 to finish the entire cycle. Okay. Where am I going? Okay, starting here. Calorimetry. So this is a simple physical chemistry setup so people can measure the heat of reaction. The setup itself is quite straightforward. Now, this is entire setup. Imagine we have, this is our reaction chamber with O2 gas in there reacting with some kind of combustible, and that combustible is placed in our sample pellet. So this entire tank here is put in a huge water bath. And this entire water bath contains several things. First, you have the thermometer to monitor how the temperature change. You have a star bar to make sure the temperature is uniform within the water bath. And then in here, you also have electrical heater, so you can manipulate the temperature change of the water bath. Also, in addition, we also have the ignition wire so that you can ignite your reaction at given point. Now in this setup, we will be calling my reactant. So my reactant in this case might contain, say, for example, in my sample pellet, maybe I have like carbon, right? So my reactant would insist like carbon, solid, and O2 gas. Right, and the product is something we formed, which is CO2. Just if we put carbon in that pellet. Also, we will call the entire water bath as K. It's a quite random nomenclature, but we just call the entire water bath as K. And this bomb itself, plus the water bath, is isolated or thermally insulated from the rest of the universe. So no, these walls are adiabatic. It's not thermally conducting. All right. So what do we want? We want to know how much heat is being released whenever we ignite the reaction to be taking place. So what's our initial state? Initial state is my reactant plus my water bath. Let's say we put it at 298 Kelvin. So before everything taking place. Right, so using our HCl example, now imagine my reactants are my H2 gas and Cl2 gas and my water bath K. All of them are in 298 Kelvin. What is our final state? Our final state here is having our product, which is HCl plus water bath, but now at a higher temperature, 298 Kelvin plus delta T. Now, I see it's a higher temperature, but if it's an endothermic reaction, you can have a lower temperature. So that's why I just put 298 plus delta T, whatever that delta T is. Right, so there's a change of temperature because of the chemical reaction taking place in the calorimeter. And then what else do we know? Some of the things we can derive. So first of all, we know that if we consider the entire calorimeter, including the water bath and the system inside, the reaction chamber inside, considering both of them, we see that delta U, or the total change of internal energy, equals to Q plus W. But in this case, my entire calorimeter is isolated, thermally isolated, or covered by adiabatic wall. So this goes to 0. Right, so that surrounding wall is also, it's also like solid, and the expansion of water is negligible. So my work is also 0 if we consider both the water bath and our reaction chamber. Yes?
The outermost wall is the adiabatic.
Yes, so this one is adiabatic. So the chamber itself is like closed, but it allows heat transfer. So that tells us we have a delta U equals to 0 for entire calorimeter. So what else do we have? This is something we know. What else do we have? Right now in this reaction, we have our initial state go to final state, which is my reactant plus water bath and 298 Kelvin, go to product plus water bath at a different temperature, right? But effectively, what we're looking for in this reaction is this process. We want reaction goes into product at the same temperature, which is 298 Kelvin. Or the other way to put it is what we want is product plus our water bath at 298 Kelvin. So we need to address what this delta T means in the energy-wise. All right, so in here, what else do we have? We know that the total delta U is 0, so the amount of energy either released or absorbed by that reaction chamber is the same as the negative of the amount of internal energy released or absorbed by the water bath. So the other way to put it is we have delta U of the reaction at 298 Kelvin equals to the negative the heat capacity of K plus P. So this one, we just call this the average heat capacity. Of both my reaction chamber, both my products and the water bath, times delta T. All right, and what is this delta U 298? This one is our internal energy change of the standard state of the reaction at 298 Kelvin. So what exactly does this mean? So let's look at an example question together. So here's the problem. It says combustion of about 2.016 gram of solid glucose at 25 degrees Celsius in an adiabatic bomb calorimeter with heat capacity 9550 joule per Kelvin gives a temperature rise of 3.282 degrees Celsius and asks us to find the delta C U naught 298. So this one, I just want to quickly mention. This one, I'm telling you, like this little C just tells you that's the delta U naught 298 for 1 mole of glucose. All right, so using the example we have, this one we have delta U naught 298 equals to negative heat capacity of my entire calorimeter times delta T. And my heat capacity here is 9550. My delta T, that's a raise of 3.282. Right, so this is just simply plugging the numbers. And you get delta U naught, and then you can translate that for 1 mole of glucose using the molecular weight of glucose. All right, so typically when we're dealing with calorimetry, the take-home message here is normally we set up our bomb calorimeter as a adiabatic bomb calorimeter, means my entire calorimeter is isolated from the rest of the world, or not typically isolated, but at least thermally insulated from the rest of the world. So delta U equals to 0. So we can simply measure the change of internal energy of the water bath, or the change of internal energy of the calorimeter to give us a measurement on how the internal energy of my reaction changes. So that's calorimetry. To take it one more step, we want to make a connection between delta H and delta U, right? So by definition, we know that enthalpy H equals to U plus PV, or at standard state, we have P naught equals to 1 bar, so we can rewrite it as delta H naught equals to delta U naught plus P delta V naught. Note that we can take this out because at standard state, pressure is a constant, so we can take it out. All right. And one of the things that we generally make, it's like a conventional approximation, is that delta V naught is typically negligible. For reactions with liquid and solid. What about for gases? Now, thinking about what does my delta V naught is for gases. First of all, what we know about the standard state of gases? We know the standard state for gases must be ideal. Right, so we can use our PV equals to nRT, or my V naught equals to nRT divided by P naught. So my delta H naught thus equals to delta U naught plus P naught times nRT P naught. Oh, and this one we're talking about delta U, then we have the only thing changing is the number of mole in this whole process. So my delta H naught thus equals to delta U naught plus delta N G RT. So note that this one, the little g here represent for the number of mole of gases. Since it's ideal, it doesn't really matter which gas it is. It doesn't matter which identity of the gas is. It only matters when you have like 1 mole of gas go to like 3 mole of gas. Or in this case, we have like 2 moles of gas go to 2 moles of gas, so the delta Ng is effectively 0, right? So depending on the nature of the reaction. Likewise, we can see one example here just to quickly see how to apply this. In this reaction, let's say we have a random gas molecule, CF2Cl, CF2Cl. We give you the heat of formation of this molecule to be a number. Can you calculate the internal energy, the standard internal energy of formation of this gas molecule, right? So what do? First thing is we write out the reaction for the heat of formation reaction, right? So we write out the formation reaction of this molecule. So here we have 2 carbon, so 2 carbon in graphite, plus we have 2 chlorine, so that's Cl2, plus fluorine, so 2 fluorine gas. And this all go to 1 molecule of CF2Cl, CF2Cl in gas phase. So for every mole of reaction, we have the number of mole of the gas to be changing over 1 mole of reaction to be 1 minus 3 equals to -2. All right, and we know what delta H is. We know delta Ng is -2. We know what R is, and this one we know what T is, which is 298 Kelvin. It's just plugging numbers to get the final answer. All right, so this takes care of our number 4, which is how to measure delta H of a reaction in a calorimetry experiment. Now, before we talk about number 1 and number 6, which is interconnecting real gas with ideal gas, let's just look at one more example, which is, what if you have a reaction that's multi-step reaction? It's just not one single step that forms your product. What if you have multi-step reaction? So this one, I'm going to go quite quickly because this part is super straightforward. It's called Hess law. So what it says is that the overall enthalpy change for a reaction is always equal to the sum of the enthalpy change for individual steps in the reaction. So I'll just do one example together, and you'll see how straightforward it is. I have one more example left there for you to practice on. The example here is Hess law in Haber process. Basically, it's a multi-step reaction. You have different delta H involved for those reactions. So in this process, the first step we have is we started from my reactant, hydrogen and nitrogen gas. And they form a molecule N2H4. Now, N2H4 will be subsequently used in the second step, and thus we call this an intermediate. Right, so my delta H of my first reaction, or standard enthalpy of reaction for my first step, equals to product delta H naught N2H4 minus reactant, so 2H2 plus delta H naught of N2. And you can check the table to get that number, and that number equals to 95.4 kilojoule per mole, and this one is endothermic. Right, and for the next step, we started from this intermediate N2H4 reacting with H2. Again, that's our reactant. And we finally get our product, which is ammonia. Or we can write the delta H naught for our second reaction to be 2 times delta H naught of NH3, so product, minus reactant, delta H naught of N2H4 plus delta H naught of H2. You can check the table to find out the second step is, delta H for the second step is 187.6 kilojoule per mole, and this one is exothermic. right? So what about the overall reaction? Now the overall reaction is just a sum of these two steps. Or delta H naught overall equals to 2 times delta H naught NH3 minus 3 times delta H naught for H2 plus delta H naught for N2. All right. Or the other way to put it is if we look at this kind of figure, looking at the energy profile, we started for our first reaction, right? So our reaction 1 goes from my reactant to product, so 2H2 plus N2, so we have delta H1 naught equals to 95.4 kilojoule per mole. And then the second step is a delta H naught for step 2, which is exothermic by 187.6 kilojoule per mole. And the overall reaction is just my reactant go to my product. So this part is not hard at all. So I left a practice problem for you to try it yourself. The most challenging part is how to quickly write the balance equation and search for the thermodynamic table to plug in those numbers. Okay, any questions on this part? All right. Okay, now back to what we have, which is how to translate the ideal gas into a real gas. So this goes to, this one to fill in the blank of my problem 1 and 6. Right, so in this entire scheme, note that number 2, 3, and 4 we have to take care of. 5 and 3 are the same. We just need to worry about 1 and 6. So let's look at 1 and 6. What do we have? When we're talking about a real gas go to an ideal gas at our standard pressure. All right, so our initial state is my real gas at standard pressure, or 1 bar at certain temperature, so at P naught. And our final state, let's say this is our initial, this is our final. Our final state is an ideal gas at 1 bar with the temperature not changing. So how do we take steps to calculate the processes? Again, for thermodynamics, whenever we're talking about a change of state function, we're always thinking about how to build a path so that I can calculate the changes. Now, the biggest difference here, the biggest challenge here, by connecting a real gas to an ideal gas, is that real gas, we have intermolecular interactions with different gas molecules, while ideal gases, the gas molecules do not interact with each other. So the most important hypothesis we're making here is if we reduce the real gas into 0 bar, and then at 0 bar, because there's no pressure, your gas molecules are not interacting with each other nevertheless. Or the other way to put it is it's reasonable to assume that all intermolecular interactions are eliminated at 0 bar. All right, so then we build the path accordingly. The first step is we have an isothermal reduction of pressure from P naught all the way to almost 0. And then we have real gas at 0 bar. Right, now we have a now we're making this assumption that at 0 bar, we can eliminate all the intermolecular interactions. So we have ideal gas at 0 bar. And obviously, the last step is to raise the pressure back from 0 bar to P naught. So we end up having what we want, right? So initially we have H of real gas at T P naught. And at the end, we have H of ideal gas at T and P naught. All right, so delta H for this process, I'm just going to keep it here and write it on the board. You can also see the workout in our annotated note. It's just easier for you to refer back to what we're saying. First step, because delta H is a state function, so we can write delta H for this process to be H ideal at T P naught minus H real at T P naught. So this is what we want, right? By building the path here, we demonstrate that this delta H must equal to delta H for the first step, which is the pressure change, isothermal pressure reduced from 1 bar to 0 bar, plus delta HB, which is at 0 bar, we're removing all the intermolecular interactions, so my real gases becomes ideal gases at 0 bar, or when the pressure is approaching 0, plus delta HC. Basically, we're isothermally increase the pressure back to its original state. So what do we have here? If we focus on process A, what is this? What the nature of this one is an isothermal pressure change. Of a real gas. All right. So, which equation should we use when we're trying to solve for isothermal pressure change of a real gas? So that goes back to what we solved before, right? So that's the isothermal pressure dependence of my enthalpy. So using this equation we derived in our chapter 4.4, we can solve for our delta HA. So delta HA effectively equal to, our initial state is P naught, our final state is 0. In there, we have negative PV alpha plus V dP. All right. So in here, there are different ways you can solve for it. We can either give you alpha as a number, or we can just give you alpha, or we can also give you the equation of state. Like for example, we can give you the van der Waals equation of state, and do you know how to solve this integral? Or maybe a simplified version of the van der Waals equation, because that one is quite complicated to solve. But nevertheless, we have a way to set up the integral and solve for the delta H change for this isothermal pressure change of this real gas. Yes? Oh yeah, of course. Better? Okay, awesome. Yeah, that's just our first step, right? So the take-home message here is just read it, what it is. It's an isothermal reduction of pressure, and we care about the change of enthalpy associated with that isothermal reduction of pressure. So naturally, we use this equation. What about part B? This one we actually mentioned a little bit. We're talking about when pressure is approaching 0. So when pressure is approaching 0, basically that means my molecules are infinitesimally, well, my molecules are super far away from each other. They're not interacting with each other. Or the intermolecular forces approaches 0. Or the assumption we can simply make is, say, the enthalpy for my real gas at certain temperature, 0 bar, is equal to H ideal at certain temperature, 0 bar. Or we can say this one just go to 0. All right. What about C? C is the isothermal pressure increase of a ideal gas. So of course you can use this equation again, but now since we have ideal gases, you know what equation of state for ideal gas is? It's PV equals nRT. Or we can take the shortcut, right? You can use this approach. It's going to give you the same answer. Or we can take the shortcut that delta H equals to my P1 T. My delta H, or for ideal gases, we have Cp, which is only a function of P, equals to dH over dt for ideal gases. Or since my temperature is not changing, my delta H for my process C must also equals to 0 for ideal gases. So one of the nice practice example you can do is try this equation for part C again, using the equation of state and this equation to show like this must be 0 for ideal gases. And as a concluding note, what we end up having is the total change, delta H, for my ideal gas at temperature and P naught, go to real gas at temperature and P naught. Because my delta HB and delta HC are just 0, that just equals to my delta HA. And do we know how to calculate delta HA? And yes, we have this integral that we can solve for, right? So we write down this integral. Initial state is P naught. Final state is 0. Here we know that alpha equals to 1 over V, partial differential of V over T at constant Pn. Or you can simplify this one into here because the volume and volume cancel out. So a small simplification. And this integral will be solvable for if we know what the equation of state is. Right, so this one is telling us that my final state is ideal gas, my initial state is real gas. If you want to transfer a ideal gas into real gas, basically just do it reversely. Add a negative in the front. Okay, I only have 3 minutes left. I don't think I should rush it, but we only have like 1 slide left for our next lecture. Let's see. Yeah, let me try go over this. This one is straightforward. So this one is talking about the temperature dependence of reaction heat. So far we went over the reaction heat equals to sum of your stoichiometric coefficient times each of the delta H of the heat of formation for all your reactant and reactant and product involved in that reaction. But this delta H of standard state delta H, that's dependent on temperature. So what does that mean? That means like if now we don't have constant temperature, we're changing the temperature. So the reaction heat might also change with respect to temperature change. So how does that happen? Now if we divide both ends by dt, right, so what we end up having is on the left, the delta H naught of the reaction over dt. On the right-hand side, stoichiometric coefficient, that's a constant, that's not going to change. On the right, we have the delta H naught for the molar enthalpy of that substance I over temperature. And in here, there are several things we know. We know that standard state of the gas is an ideal gas. So we have Cp equals to dH over dt at constant P, or at constant pressure, if we specify pressure to be 1 bar, we have Cp naught equals to dH over dt. Or effectively, we can write our standard heat capacity change of the reaction. So this is the delta Cp naught. So that's the standard heat capacity change of the reaction. This one to be equal to the stoichiometric coefficient times each of the standard molar heat capacity. And also typically in our coefficient, it will give you this Cp naught of that species, the standard molar heat capacity of a certain substance at 298 Kelvin or some other temperature in your thermodynamic table. Just some information to look after in the thermodynamic table. And let's see. Okay, and alternatively, we can have also like an expression for this standard molar heat capacity. So occasionally we'll also give you a equation. It's basically an expanded equation that's dependent on temperature. Okay, I'm running out of time. There is one example in the next page. You can try it yourself and see how to use appendix data and see, assuming the Cp naught is not changing with respect to temperature, can you estimate the delta H naught at 1000 degree for the reaction given? So the answer is also posted in our annotated note. All right, that's all. So next Monday, we'll pick up our conventional entropy, third law of thermodynamics. I'll see how much we go with respect to the Gibbs free energy. And I'll see you next Monday.